Okay, we are going to talk now about phase changes. Really exciting stuff. Actually, it's not too bad. It sort of ties together some of the things we've been talking about as far as intermolecular forces and then going back to some of the delta H stuff that we've talked about in the past. So bear with me. I'm going to go through this fairly quickly. I'm going to assume that you know a lot of this already. As far as these different phase changes, we're talking about changes in state of matter. Okay, same thing. And this is basically a chart just showing all the different names that we have for these things. So solid going to a liquid is melting. We know that. Liquid going to a solid is freezing. Liquid going to a gas is called vaporization. There are two ways that can happen, evaporation and boiling, and we're going to talk about both of those. Condensation is when a gas changes back into a liquid. Sublimation and deposition are the two you might not be as familiar with. Sublimation is when a solid changes into a gas. Deposition is when a gas changes back into a solid. Okay, so those are your different phase changes that you can have. And I'm pretty sure we talked about all those last year, so I think you should be good there. Now, what I want to talk about here, and in just a little bit of detail, because I'm pretty sure we did this last year as well. I want to talk about the way the intermolecular forces change for each of these types. Now, I want to be very clear here about what I'm talking about. When I say intermolecular forces, because I think some of you struggled with this when we took this test. Intermolecular forces, what I am talking about is the force of attraction between two water molecules, for example. Okay, so example of this might be like this: the attraction of this hydrogen for this oxygen. Okay, that right there is an intermolecular force. It's the force between two water molecules. Okay, now this right here, the bond between that oxygen and hydrogen, that is a covalent bond. Okay, that's considered an intramolecular force. The only way to break that bond is by doing a chemical reaction. Okay, but you can break this bond right here between the two different hydrogen, or the two different water molecules, by a physical change such as melting it or boiling it. Okay. All right. So when we talk about melting / freezing, I'm going to talk about melting specifically. We'll talk about going from a solid to a liquid here. Okay. And then you can just think about this in reverse to go the other direction. So when something melts, when we start out, the solid particles, whatever they are, the solid molecules, are very attracted to one another. The intermolecular forces hold them in place. And they just vibrate. Okay? So then as it melts, as you give energy to these solid particles, as energy is added, the intermolecular forces, okay? Or I guess intermolecular bonds is what I should probably say here. So IM stands for intermolecular. The intermolecular bonds start to break and reform. Which allows the molecules, allows the particles to move past one another. Okay, so hopefully that makes sense. What's happening here is, like looking at our water example up at the top here, it's giving these two enough energy so that these bonds can temporarily break. They're moving around fast enough now that they can't be, or they've got enough energy that they want to be moving around, so they can't be held in one spot necessarily. But they're still so close together that these intermolecular forces are really important. And so what happens is they will move past one another, be attracted to each other, and form these hydrogen bonds for a moment. And then those will break as they slide past one another, and then be attracted to a different water molecule, and then that attraction will break, and then so on and so forth. And that's how a liquid works, okay? Now, when something vaporizes, okay, and again, we're going to talk about the liquid to gas here, and you can just think about this in reverse. So, by the way, if you're thinking about this top one in reverse, the freezing process, the way that that works, obviously, as something freezes, it releases energy into the surroundings. So these particles are going to give up some of their energy. They start moving slower, and then those intermolecular forces become strong enough again to hold them rigidly in place. Okay. So then with a liquid going to a gas, the way that that works is that the intermolecular forces start to break completely. Okay. Now, I say completely, I'm assuming this is changing into an ideal gas here. Okay. We know that some of these intermolecular forces still have some influence on the particles, but not a lot. Especially in a normal environment, we can say they break completely. So, liquid particles, again, well, we already know what the liquid particles are doing because we wrote it up there. They're breaking and reforming, okay? So, as energy is added to a liquid, the particles have enough energy to, I'll say completely, escape intermolecular attractions and act independently. Sorry about my handwriting there. Okay, so that's the idea. We add energy to a liquid, and now these particles that are moving past one another but still very attracted to one another, eventually they get enough energy and they can completely escape those intermolecular forces. Okay, and then they go away from the liquid and they can act independently as their own individual particle. Okay, now again, you put gas particles close enough to one another and cool them down enough, those intermolecular forces start to be significant, and if you do that enough, then they change back into a liquid. They condense, okay? All right, sublimation and deposition. All that's happening there is, and again, for sublimation, that's the one that we'll focus on here, the gas, or sorry, not a liquid either. Solid to gas, that's sublimation. So, the intermolecular forces that are completely, maybe I'm going to say, that are holding molecules in place are completely broken all at once. Allowing molecules to escape as a gas. Okay, so that's the idea there. And then deposition is the opposite. It would go from not really having any intermolecular forces to speak of directly to having these rigid intermolecular forces. It just skips the liquid stage is what's happening there. Okay? All right, so there's our phase changes. The energy change associated with this, as you might imagine, it takes a lot more energy to vaporize something than it does to melt it. And so you look at any of these things, butane, diethyl ether, water, mercury, it takes a lot more energy to change them into a gas than it does to change them from a solid to a liquid. Okay. Heat of fusion is the energy required to change a solid at its melting point to a liquid. So, for example, water, its melting point is 0 degrees Celsius. Okay. So at 0 degrees, it's the amount of energy it takes to melt it, to break some of those intermolecular forces. And then heat of vaporization is the heat it takes or the energy that it takes to change a liquid into a gas. Okay, this is called the heating curve, and this is the heating curve for water. There are also cooling curves that go in the opposite direction as something is cooling down, okay? But this is a heating curve for water, and what this is showing is the temperature change that water undergoes as heat is given to it, okay? And so what you're going to notice here, we're starting point A here. We're starting with water at negative 25 degrees Celsius, okay? Now, as heat is being added, that's going to heat up until it gets to 0 degrees Celsius, point B right here. And then you've got this section of time right here where the temperature doesn't change at all, okay? And that's kind of weird unless we think about what's going on with the intermolecular forces there, okay? Once this thing gets up to 0 degrees Celsius, this ice is now ready to melt, okay? It's at the temperature where it could start melting. Well, you've got to give that ice some energy in order for it to be able to break those intermolecular forces enough that these particles can start sliding past one another. Now, that doesn't take a lot of energy because they're still close. They're just sliding past one another now instead of being held rigidly in place. That doesn't take a lot of energy, okay? But that's what's going on from B to C, and that's why the temperature doesn't change, because the heat is now not going into changing the temperature of the average kinetic energy of the particles. Now it's changing the attraction of the particles for one another, the intermolecular forces. Okay. From C to D, what we're doing is we are increasing the temperature again. Okay, so we're adding heat, and this is going from 0 up to 100. Okay. Now, at 100 degrees, this thing is going to boil. Okay, and this for a long time will not change temperature. Okay, because all of the energy is then going into breaking completely those intermolecular forces, and as you can imagine, that takes a little bit more time and a little bit more energy than just changing it from solid to a liquid would take. Okay, sorry, hang on just one second. Okay, so let's see, where were we? And then from E to F, obviously, again, the temperature is starting to change as we continue to add heat. So this will happen with water. If you heat up water, if you have a block of ice and you put it on the stove, I think that's the easiest way to think about this, and start adding heat to it, constant amount of heat, and you measure the temperature. As long as there's an ice-water mixture, this thing is going to be at 0 degrees Celsius or very close to it, okay? And then again, the hottest you can really get the liquid water is about 100 degrees, because at that point it starts to boil, and it's not going to change temperature once it starts to boil. It's going to be right at 100 degrees the whole time until you have it all changed to steam, and then if you have some way to trap the steam, then you could heat up the steam or the water vapor higher than 100. Okay, but the temperature of the substance does not change during the phase change. All that energy is going into making the intermolecular forces break between the molecules. Okay, all right. So the question now, at what point on the heating curve does the greatest amount of liquid water exist? Okay, you might think, oh, I don't know, maybe right here in the middle somewhere of the liquid phase. Well, the thing is, we know that water evaporates also, right? Oops. Evaporates. So some evaporation is going to happen as this thing is starting to heat up towards its boiling point. Okay, and the closer you get to the boiling point, the more of it is going to evaporate. So the greatest amount of liquid water is probably going to exist right here at point C, where all of the ice has just melted, but it hasn't really had a chance for any of the liquid water to evaporate yet. Okay. All right, now this is a fun problem. This is wanting to know the heat change or the enthalpy change if we take 1 mole of ice at negative 25 degrees Celsius and we change that into steam at 125 at a constant pressure of 1 atmosphere. Okay, now this is going to take us back a little bit. They're talking about specific heats here, so that might be your hint that we're probably going to use this equation right here. This is from a while ago, okay? But Q at constant pressure, which we're talking about here, Q is equal to delta H. Delta H is the enthalpy change, okay? And that's equal to C times M times delta T. C is specific heat, M is the mass, delta T is the temperature, okay? And so we're probably going to need that equation here. Now what we have to do, essentially, is we have to find the delta H of the temperature change from negative 25 degrees Celsius to 0 degrees Celsius, okay, because it takes some energy to do that. Then we need to find the delta H. Once we're at 0 degrees Celsius, we need to find the delta H of fusion, okay, which they actually already give to us. But the delta H of fusion, that's the amount of energy it takes when something's at 0 degrees, or when the water is at 0, to go from a solid into a liquid, to melt it, essentially. Then, once it's melted, we're going to have to calculate the delta H that it takes to go from 0 degrees Celsius to 100 degrees Celsius. Okay, and then once we're at 100, then we're going to have to vaporize this, change it to a gas. Okay, so that's going to take some energy. And then, once it's a gas, we're also going to have to use some energy to get it from 100 up to 125. So we need to calculate all of these different delta H's and then basically add them together at the end. Okay. So to go from negative 25 to 0, I'm just going to use the C times M times delta T equation because that one involves a temperature change. Okay. So my C here, my specific heat for ice, is 2.09 joules per gram times Kelvin. Now, just for the sake of room, I'm not going to put my units in here, but I need to pay attention to them. Okay. 2.09 joules per gram times Kelvin. Then I need to multiply that by the mass of the water. Well, the thing is, we don't have a mass, we have a number of moles. But 1 mole of water, all I have to do there is multiply that by the molar mass, right? There are 18 grams of water in 1 mole, so this is going to be 18 grams, okay? I guess 18.0 grams, technically. Okay, and then my temperature change here is going to be 25 Kelvin. If I'm going from 25 degrees Celsius to 0 degrees Celsius, that's a temperature change of 25 Celsius. But because the Celsius and Kelvin scale are directly related to one another, that's also a change of 25 Kelvin. Okay, so that's going to give me my heat of the change from negative 25 to 0. Now, something I got to be careful of here. You know what? I'll change these delta H of fusion and vaporization. I'll change those to joules. Okay, because these are given to us in kilojoules per mole. All right. And these up here are the specific heats are given to us in joules. So we need to make sure that we keep our units the same. So now the delta H of fusion, it's 6.01 kilojoules per mole. Okay. Now we only have 1 mole of water here. Okay, so that's easy. That's just 6.01 kilojoules. So if I change that into joules, I just multiply that by 1,000. So that's going to be 6,010 joules. Okay. Now moving on to the 0 to 100, I'm going to use the specific heat of water now, because now I have liquid water. So that's going to be 4.18 times, again, we still have 18.0 grams, times our temperature change now is 100. Okay, and that's going to give us our number of joules there. Our delta H of vaporization, 40.67 kilojoules per mole. Again, this is 1 mole of water we're talking about here, 1 mole of H2O. So I just need to change this to joules, 40,670. And then this bottom one here, I'm going to take the specific heat of water vapor, which is 1.84 times 18.0, which is the mass, times the temperature change, again, is 25 degrees here, from 100 to 125. Okay. So then once I total all of these up, that's going to give me, well, I guess I need to calculate them first. So this one right here, I'm getting 940.5, and that's joules. Okay. And then 6,010, already got that taken care of. 8 times 18 times 100, 7524 joules. And then 1.84 times 18 times 25, that's 828 joules. Okay? So then I just need to change well, I've got them all in joules right now, so I'll add them up first, and then I need to probably change that back to kilojoules because it's going to be a large number. So you just need to add all of these together. And that's going to give you the total amount of heat that you would need to do this entire process. It's going to be 55,972 joules. Okay. Equals, now let's think about our sig figs here. I think we've got 3 sig figs. No, maybe 2 sig figs. Yeah, just 2 sig figs here because of our temperature. So this is going to be 56,000 joules, which equals 56 kilojoules. Okay, so that's our answer on that one. All right, moving on. Vapor pressure. At any temperature, some of the molecules of a liquid are going to have enough energy to escape. Okay. Obviously, at higher temperature, more of those molecules are going to have energy to escape, and that's evaporation. Okay. So notice at the higher temperature here, this is kind of like one of those speed distributions from the last unit, but this time it's showing the amount of energy that these things have, which I guess is related to temperature. So really it is kind of like a speed distribution here. But this right here, if you notice, at the higher temperature, more of the particles are going to have that minimum kinetic energy needed to escape, okay? And then at a lower temperature, less of them will, even though some of them will for both, okay? But the higher you get your temperature, the more of them are going to have enough energy to escape. That's kind of goes without saying, okay? And again, I just said that. Okay, so vapor pressure, as these molecules evaporate, as these liquid molecules evaporate and become a gas, they start to exert pressure on their surroundings, okay? And so you can look at this this manometer here. This ethanol, all liquid at first, and see how the pressures are equal. The level of the mercury is equal on both sides of this tube at the beginning. Well, what's going to happen is these liquid molecules are going to start to evaporate, and then once you have all the gas molecules in here, now there's a difference in pressure. The vapor pressure has increased the overall pressure that's inside the manometer, okay? And then what's going to happen eventually is they're going to reach a state of equilibrium, okay? And what that means is that the rate of the molecules evaporating is going to be equal to the rate of the gas molecules condensing back into a liquid, okay? So it's not that they stop, okay? These molecules are always going to be moving. Some of them are always going to be evaporating. Some of them are always going to be condensing. But it just means that they are evaporating and condensing at the same rate. So now you have an equilibrium, okay? And you can actually watch this happening. If you have a manometer, as this liquid ethanol starts to evaporate, you're going to start to see the level of this mercury going down, and eventually it's going to stop, okay? At that point, you can know that it has reached equilibrium. The number of liquid particles evaporating is equal to the number of gas particles condensing at that point, because there's no net change in the pressure. Okay, now you need to understand this, and we're going to go over this on a couple of questions on the AP packet this time. Vapor pressure of a liquid does not depend on surface area, just temperature, okay? So if the temperature stays constant, the vapor pressure stays constant, period. All right, now I'll show you a couple examples of that. Okay, boiling point of a liquid is the temperature at which its vapor pressure equals atmospheric pressure. Okay, so for something to boil, it has to overcome a couple of things here. So you've got liquid water in a beaker, all right? In order for that water to escape as a gas, first thing it has to do is it has to overcome intermolecular forces within the liquid itself. There are water molecules that are pulling on that, trying to keep it from escaping, okay? That's the first thing it has to do. The second thing it has to do is it has to have enough energy to counteract the atmospheric pressure pushing down on it, okay? And so basically that's the boiling point, okay? That's the temperature at which the vapor of the liquid has a high enough vapor pressure for its molecules to escape as a gas, okay? And everything's going to have a different normal boiling point. Normal boiling point is just when we're at 1 atmosphere of pressure, okay, which is 760 millimeters of mercury, or is 1 atmosphere, okay? So for diethyl ether, for example, when it's at 1 atmosphere of pressure, you need to heat it up to 34.6 degrees Celsius before its particles have enough energy to escape as a gas for it to boil, okay? Now, we're saying for all of its particles, okay? The boiling point is when all of its particles now have enough energy to escape as a gas, and they eventually will in a fairly short amount of time. Evaporation, some of the particles are going to be able to escape as a gas at any temperature, okay? But this is when you're actually boiling, when you have bubbles coming up from the bottom of your solution, okay? So the normal boiling point is the temperature at which your vapor pressure is 760 torr. Okay, what that means is, again, looking back at our beaker example, I'll make it a little bit smaller here. So I've got this liquid, okay? If I've got 1 atmosphere of pressure pushing down on it, then this liquid is going to have a vapor pressure of 760 torr before its molecules have enough energy to get away. All right, so the point at which the vapor pressure of the liquid is 760 torr is the normal boiling point. Okay, use the figure on the right to estimate the boiling point of diethyl ether under an external pressure of 0.80 atmospheres. So first thing we got to do, because this thing is in torr, we need to convert this. So 0.80 atmospheres times 760 torr. That's going to give us our pressure in torr. And that's 608. Okay, so then we'll come over here to about 608 torr, see where it hits the diethyl ether line, right about there, and then we'll just trace that down. That's that tracing. I'll trace that down to where it hits the temperature line, and it looks to me like it's pretty close to 30, maybe a little bit closer to 20. So I'm going to say like maybe 29 or 30 degrees Celsius, okay, would be its boiling point when it has 0.80 atmospheres of pressure on it, okay? So reduce the pressure, you reduce the boiling point. All right, phase diagrams. We're getting close to being done here. Sorry this is taking so long. Phase diagram is basically a graph that shows at certain pressure and temperature conditions what state of matter is whatever substance you're talking about going to exist in, okay? And so it also shows the places where there's equilibrium between the phases, like where a solid and a gas would exist in equilibrium, or where a liquid and a gas or a solid and a liquid would exist in equilibrium, okay? So here's kind of how to read this. This line right here, the line that's being circled, is the liquid-vapor interface. And I almost said interface, that's biology, interface. So what's happening here, between this phase right here, or right on this line, I guess, you've got equilibrium between a liquid and a gas, okay? If you have constant pressure, and you heat this liquid up, obviously it's going to change into a gas eventually, okay? If you have, if you hold it at a constant temperature and you decrease the pressure, that's another way to get something to go from a liquid to a gas, which kind of makes sense. If you decrease the pressure over a liquid, its particles are going to be able to escape as a gas more easily, okay? The triple point right here, that is the point where solid, liquid, and gas all exist in equilibrium, and that this only happens at one specific temperature and pressure for every substance, okay? There's only one perfect pressure and temperature where all three of those are going to exist in perfect equilibrium. And then at the critical point right here, anything above the critical point, you're putting the gas under high pressure and high temperature, okay? So these gas particles, or liquid particles, whatever they are, they're moving incredibly fast at this point, but they're also under a high amount of pressure, so they're still very close together. So it's difficult to distinguish, are these acting as a liquid or are they acting as a gas at this point, okay? So above that critical point, it's called a supercritical fluid because it's hard to tell, is this a liquid, is this a gas? Okay, each point along the line that's circled right now is the boiling point of the substance at that pressure. So if you want to know the boiling point of a substance at this particular pressure, you just see where it hits the line, trace it down to that temperature, and that'll tell you the boiling point at that pressure. Okay, so it's a useful diagram. Then we've got the solid-liquid line here. Okay, that's the one that's circled now. And that's the line between liquid and solid. Okay. The melting point can be found along this line. Now again, notice if I have a solid and I hold the pressure constant and I increase the temperature, then it's going to change into a liquid, okay? This might seem a little bit stranger here, but under certain conditions, if you're close enough to the melting point, then you could actually hold the temperature constant and decrease the pressure, and change it into a liquid, okay, for most substances. Now, water is an exception to that, as we'll see in a minute. But that's kind of an interesting idea, decreasing the pressure to melt something instead of increasing the temperature. And it doesn't work nearly as well as it does for changing a liquid to a gas. But it can work. Below the triple point, the substance can't exist in the liquid state. Okay, so below that triple point, the only things that can happen is a solid going directly to a gas or a gas going directly to a solid. Okay, which is kind of what's going on with dry ice, which we'll talk about in a second. So this is a phase diagram for water. High critical temperature and high critical pressure. Okay, and this is due to strong van der Waals forces. Now remember, van der Waals forces are just that's the general name for all intermolecular forces. The one that's really responsible for that is the hydrogen bonding. Okay. So, I mean, you can sort of look at this. A couple of weird things about water. The slope of the solid-liquid line is negative. Okay. So what that means is, let's say that you've got liquid water that's just above the melting point. If you decrease the pressure on that liquid water, it's actually going to change back into ice, which very unusual, okay, but that happens for water, so kind of an interesting thing. Carbon dioxide. The interesting thing about carbon dioxide is at normal pressures, it goes directly from a solid to a gas. So at 1 atmosphere of pressure, notice here, it skips the liquid phase completely. The only way to get carbon dioxide to liquefy is actually to get it up, above 5.11 atmospheres of pressure. So if you have like 10 atmospheres of pressure, you could get it into the liquid state for a little while before it progressed on to the gas phase. Okay. Also notice here that CO2 fairly low critical temperature and pressure, okay, relative to other things. 73 atmospheres is still a lot of pressure, but especially the 31.1 degrees Celsius, that's a pretty low temperature, and that's its critical temperature. So CO2 is actually an ideal supercritical fluid, and the reason that this works, or the reason this is useful, is because it makes a good non-polar solvent. And we're going to talk about this a little bit more in a couple of days. But we talked about a little bit last year, I think. Polar things dissolve other polar things, and non-polar things tend to dissolve non-polar things. And so what that means here is CO2 is non-polar, so it's good at dissolving things that water can't, like caffeine. So if you've got this supercritical CO2, okay, it's a very dense liquid, or however you want to think of a supercritical fluid. But you're able to take the caffeine, extract the caffeine from something, and move it to another place using the CO2, the supercritical fluid. Because the caffeine will dissolve in the CO2 and some other things won't. Okay, so last couple of problems here and then we're done with this. Describe any changes in the phases present when H2O is kept at 0 while the pressure is increased from 1 to 5. Okay, so we're going from here up to here. I mean, this is fairly straightforward, but what's going to happen here, as the pressure is increased, it's going to go from a gas to a solid first. Okay, kind of interesting. And the name for that is deposition. So that's what they really want, is the name of the phase changes here. And then, eventually, you get the pressure high enough, then it's going to re-liquefy. Okay, so it's going to change from a solid to a liquid. And solid to a liquid is melting. Which, again, kind of strange, but that's what's happening for water. Okay, water's just a little bit weird. You increase the pressure on solid water, and it liquefies. That's not normal. Most things, you increase the pressure on them and they solidify because you're pushing them closer together, and so then they end up vibrating in place, but not with water. Okay, and then the next one here, we're going to go the other direction, horizontal, from 6 to 9, and we want to describe the phase changes that take place as the temperature is changing. So first thing it's going to do is it's going to go from a solid to a liquid. So that's going to be melting. And then it's going to change from a liquid to a gas. Now this is more straightforward. This is the more normal process. We don't think about changing the pressure as much as we think about changing the temperature of these things, but that's what's going to happen when you increase the temperature of water. And we kind of knew that already. It goes from a solid to a liquid to a gas. Okay, that is it for today. So again, sorry that went so long. Hopefully it all makes sense. And starting next time, you guys can come in and watch this in the morning if you would like to. Okay, see you in